Here's an exercise that involves both the principle of conservation of energy and also the conservation of linear momentum. A pile drive hammer of mass 0.8 tons falls through a distance of 2.5 meters and is assisted by an externally applied downwards force of 1 kilonewtons, acting over the distance of 2.5 meters. If the hammer strikes a pile of mass 200 kilograms without rebounding and drives the pile 0.15 meters into the ground, we've got to calculate the average resistance, that's the force, the ground exerts on the pile. So we're going to adopt a three-stage process here. In the first stage of the process, we're going to consider the pile driver hammer falling through a height of 2.5 meters. We're going to calculate the velocity on impact, in other words, just as the hammer is about to strike the pile. And in the second stage of the process, we're going to apply the conservation of linear momentum to help us find the velocity after impact. And for stage 3, we'll revert back to using energy to find the force exerted on the pile as it moves into the ground by calculating the work taken out of the system. So taking the information from the question, so the pile driver hammer mass, capital M, is 800 kilograms. That's also M1 later on in the calculation. The height, H, through which the hammer falls is 2.5 meters. The externally applied force on the hammer, capital P here, is 1000 newtons. The mass of the pile that's being banged into the ground, lowercase m, is 200 kilograms. Later we'll denote that as M2 in our momentum equation. And notice the distance the pile moves in the ground, S, is 0.15 meters. So stage 1, we're going to calculate the velocity of the pile driver on impact. To do this, we're going to consider an energy balance. Notice in our diagram, the datum is taken at the top of the pile. So from an energy balance, at position 1, 2.5 meters above the datum, we have initial energy, and any work into the system must equal at position 2 here, the final energy plus any work out of the system. So the pile driver hammer here at position 1 has potential energy relative to the datum, so mgh, and work is being done on the hammer as it moves from 1 to 2 because we've got the external force P applied constantly over the distance of 2.5 meters. So we add the P multiplied by H as the work into the system. In position 2, when the hammer is just about to strike the pile, there will be no potential energy because the hammer will actually be on the datum. There's no work out of the system here because there's no frictional forces mentioned in the question. So there'll just be kinetic energy on impact, a half mv squared. So in this equation, we know all the terms except for the v, the velocity on impact, so we can rearrange the equations and multiply both sides by 2, divide both sides by m. We can find v squared, and then square rooting both sides, we can find v. Inserting the appropriate values into this equation and square rooting, we find that the velocity on impact is 7.436 meters per second. Exercise 1D continued. Part 2. We're now going to calculate the common velocity after impact, and to do that we'll apply the conservation of linear momentum. So our momentum equation is m1u1 plus m2u2 is equal to m1 plus m2 multiplied by the common velocity v. We're assuming here, as stated in the question, there's no rebound, so as the hammer hits the pile, both are joined together and will move down into the ground. But at this particular point, we're just considering the impact itself. So before impact, the hammer and the pile have different velocities. The hammer is moving with the velocity 7.436 meters per second, and the pile will be stationary, so U2 is 0. To rearrange to find the velocity after impact, we simply divide both sides by the m1 plus m2. Inserting the values into the equation, and again noting that the U2 is 0 here because the pile is originally stationary, so that term will disappear. We find that the velocity after impact is now 5.949 meters per second. That's the common velocity. The hammer and the pile are assumed joined together. Exercise 1D continued. Part 3, we're going to calculate the ground resistance. That's the force F applied from the ground that slows the pile down to rest. So considering the energy balance between position 1 here, when the pile and the pile driver are moving with the velocity 5.949 meters per second, and at a height 0.15 meter above the datum shown here. And then position 2 later on is when the pile and the pile driver have moved into the ground 0.15 meters and are now stationary. Final velocity 0. So considering the energy balance of initial energy and any work into the system is equal to the final energy and any work out of the system. So using the notation of capital M is the mass of the pile driver, and lowercase m is the mass of the pile, we can see that at position 1 here, the pile driver has potential energy above our datum and also kinetic energy because it's moving with velocity. Likewise, the pile also has potential energy and kinetic energy. In position 2 here, the pile and the pile driver are now stationary. They've moved into the ground 0.15 meters. So all the energy at position 1 on the left-hand side of the equation is all now being transferred into work out of the system. In other words, force multiplied by distance. And the force here is applied from the ground on the pile to bring it to rest. So rearranging the equation to find force F, we simply divide throughout by the distance S. Do note in this question though that height h and distance S travelled are actually the same thing. They're both 0.15 meters. All we do now is put the numbers into the equation and evaluate. And we find that the final force is 127,779 newtons, or 127.78 kilonewtons. So you can see this pile driver problem is quite a complicated problem, and we're analysing it in 3 stages, applying energy methods first of all to find the velocity on impact, linear momentum methods to find the velocity after impact, and then energy to find the work out the system and essentially find the force applied to bring the pile to rest. I would encourage you to revisit exercise 1D at your own pace, fully understand the solutions, and then attempt the questions shown on the following slide. I'll leave you with these 2 questions. Question 1D is very similar to the previous exercise. You need to determine the average resistance of the ground to the movement of the pile. And question 2D is similar, but it wants you to ultimately find the distance the pile will be forced in the ground, because in this case you're given the ground average resisting force in the question. Answers are shown in the brackets for your reference. Here's the bibliography used to help generate this presentation.